All right, ready to dive into some seriously influential writing on system design.
Always up for that. Especially when it's something as packed with insights as Butler Lampson's Hints and Principles.
You've definitely got that right. It's like a master class squeezed into a handful of pages.
And you want us to really unpack it, right? Find the nuggets of pure gold.
Exactly. Our listeners are hungry for the kind of wisdom that can level up their tech game.
What I find really interesting about this paper, though, is that it's not just for hardcore engineers. It speaks to anyone who uses technology, which is, well, everyone.
Because at the end of the day, it's about making systems that people actually enjoy using.
Right. Exactly. It's about bridging that gap between the ones and zeros and the human experience.
And Lampson has this really neat way of summarizing his design philosophy. He calls it STEADY.
Steady. I'm intrigued.
So STEADY stands for simple, timely, efficient, adaptable, dependable, and, get this, yummy.
Yummy. Okay, now you have to explain that one.
I know, right? When you think about computer systems, yummy isn't usually the first word that comes to mind. But Lampson's point is that a well-designed system should be a joy to use. It should be so intuitive, so elegant, that it just feels right.
Ah, I get it. Like a perfectly crafted tool that just melts into your hand when you use it?
Exactly. But it all starts with that first principle. Simple. Lampson is adamant that simplicity is the foundation of everything else.
It's like they say, keep it simple, stupid, though maybe without the stupid part.
Right. But seriously, it's about stripping away the unnecessary, focusing on the core functionality and making sure that's rock solid.
Makes sense. But how do you balance that with the ever-increasing demand for more features, more power? It seems like every piece of tech these days is trying to be all things to all people. It's a constant struggle. But Lampson would argue that simplicity is actually the key to achieving those other goals. Efficiency, adaptability, even that yummy factor we were talking about. Because when you strip away all the bloat, you're left with something that's easier to understand, easier to maintain, and ultimately more enjoyable to use.
Okay, I'm starting to see the light. So it's not just about minimalist design, it's about clarity of purpose. Knowing what your system is supposed to do and doing it really, really well.
Exactly. And that's where Lampson introduces this really cool concept he calls the rocket science pattern.
Rocket science.
Oh.
Okay, you've got my attention. Tell me more.
So imagine you're building a rocket. You know there's one part that absolutely has to work perfectly or the whole thing goes boom. That's your rocket science.
Right, that makes sense. It's the critical component, the one that demands the most attention.
Exactly. So you pour all your effort, all your ingenuity into making that part sing, but everything else, every other system, you keep as straightforward as possible. Because complexity breeds chaos, especially when you're talking about something as intricate as a rocket or a computer system for that matter.
Exactly. And Lampson argues that this principle applies to all sorts of systems, from operating systems to databases to web applications.
Okay, I'm sold on the theory, but can you give me a concrete example? How does this rocket science idea play out in the real world?
Well, take the inode structure in file systems.
Inodes. I remember those from my computer science classes. They're how the system keeps track of all the files, right?
Exactly. And they need to handle files of all sizes, even gigantically huge ones, and they need to do it efficiently. So the core design of the inode is incredibly elegant. It's like the rocket science of the file system. But because that core is so well defined, you can add all sorts of extra functionality around it without sacrificing performance.
Like what kind of extra functionality are we talking about?
Well, for example, you can use extents to manage large files more effectively. Or you can implement copy-on-write functionality to improve performance and data integrity.
Ah, I see. So the core remains solid, but you can build upon it and adapt it to different needs without compromising the fundamental design.
Exactly. But then Lampson throws in this really interesting curveball. He talks about the GEC Alpha versus the Pentium Pro.
No, those were two processors that were battling it out back in the day. I remember the Alpha was supposed to be the super fast, streamlined RISC chip.
Exactly. It was designed for simplicity and raw speed, but it ultimately lost out to the Pentium Pro, which was a much more complex CISC processor.
Wait a minute. Are you saying that simpler doesn't always mean better?
That's exactly what Lampson's example seems to suggest. The Pentium Pro, even with all its complexity, delivered such amazing performance that it won out in the marketplace.
So context is king. Sometimes a bit of complexity is justified if it delivers the goods.
It seems so. There's no one-size-fits-all answer, no magic bullet. You have to consider the specific requirements, the trade-offs, the overall goals.
So how does this apply to the whole simple is better mantra? Should we just throw simplicity out the window if it means we can squeeze out a bit more performance?
Not at all. Lampson's point is that simplicity shouldn't come at the expense of functionality. It's about finding that sweet spot, that balance between elegance and practicality.
So a system could be incredibly complex under the hood, but as long as that complexity translates to a smooth, intuitive experience for the user, then it's still achieving that goal of simplicity.
Precisely. It's about hiding the complexity, abstracting it away so the user can focus on what they want to achieve without getting bogged down in the details.
Okay, I'm with you so far. So simple might not always mean easy to build, but it should always translate to a better, less frustrating experience for the user. Would you say that's the main takeaway here?
Absolutely. And to illustrate this point, Lampson actually uses Windows Vista as a cautionary tale.
Windows Vista. Now there's a blast from the past. Didn't it have a bit of a reputation for being, shall we say, a tad complex?
That's putting it mildly. It tried to do too much, introducing all sorts of ambitious new features like a universal file system, a revamped graphics engine, and a completely overhauled networking protocol.
Sounds like they were aiming for the stars. What went wrong?
Well, all those grand ambitions ended up creating an incredibly complex system that was notoriously buggy, slow, and resource intensive.
So a classic case of over-engineering.
Exactly. And in the end, a lot of those ambitious features were either scaled back or scrapped entirely because they simply didn't deliver enough value to justify the added complexity.
Talk about a system design nightmare. It's a painful reminder that ambition is great, but practicality matters.
Absolutely. And it all circles back to that fundamental principle. Simplicity is key.
Finding that sweet spot between aiming high and delivering a system that actually works, that's the real challenge, isn't it?
It sure is. And it all starts with a solid foundation of simplicity. So we've spent a good chunk of time talking about the importance of simplicity, which makes a lot of sense. But what about efficiency? Those two things don't always go hand in hand, do they?
You're right to point that out. They're definitely related, but not the same thing. Lampson's take on efficiency is really interesting. It's about more than just raw speed or squeezing every last drop out of your hardware.
Which is what a lot of people focus on, right? Like how many megahertz or gigabytes can we cram into this thing?
It's tempting to get caught up in the numbers game, but Lampson would say, hold on a second, what are we actually trying to achieve here? He wants us to focus on the smartest, most cost-effective way to get the job done.
Cost effective. I'm hearing echoes of simplicity there. It's not just about technical efficiency, but also about using resources wisely, right?
Absolutely. And sometimes that means resisting the urge to over-optimize every little thing. In fact, Lampson argues that sometimes good enough is actually better.
Good enough. Okay, now you're speaking my language. I'm all for working smarter, not harder, but how do we know when we've hit that good enough point?
It's a balancing act, for sure. But think about it this way. If a website takes an extra half second to load, but it's incredibly reliable and easy to use, are you really going to notice that half second?
You know what? Probably not. Especially if the alternative is a site that loads instantly but crashes every 5 minutes.
Exactly. And there's even a certain elegance to that approach, wouldn't you say? It's about focusing on what really matters, on delivering a smooth and predictable experience, even if it means sacrificing a few milliseconds here and there.
Okay, I like where you're going with this. So how does this apply to something as complex as, say, the internet itself?
Well, Lampson actually uses the web as a prime example of this good enough philosophy in action. Think about it. It's designed to tolerate failures. If a page doesn't load, you just refresh or try again later. No big deal.
You're right, I do that all the time without even thinking about it. But isn't that kind of, well, flaky?
On the surface, maybe. But that inherent flakiness is what makes the web so robust and adaptable. Like those springy toys, right? They can bend and bounce back because they're not rigid.
You mean those ones that you can't seem to break no matter how hard you try?
Exactly. And Lampson actually uses that very phrase, flaky, springy parts, to describe this kind of system design. He argues that these systems are better equipped to handle change and evolution, which is essential in a world where technology is constantly in flux. And this whole idea of embracing imperfection ties into the concept of hints in programming.
Hints. Now, are we talking about little messages for the programmers or something else entirely?
Not quite. A hint in this context is like a shortcut that saves you time if it's correct, but there's a backup plan in case it's not. It's about optimizing for the common case while still being prepared for the unexpected.
Got it. So it's kind of like having a plan B in your back pocket, just in case.
Precisely. Think of network routing, for example. Routers use hints to quickly forward packets of data to their destinations. If a hint is wrong, no problem. The system just reroutes the packet using a different path. It might take a bit longer, but the data still gets through.
So it's about being resilient, not necessarily perfect. I like
Uh-huh.
that.
And that brings us to another crucial aspect of system design: concurrency. This is where things get really interesting.
Concurrency, isn't that all about making things run faster? Like spinning up multiple processors or cores?
It's definitely part of the picture, but concurrency is really about managing the complexity of systems where multiple things are happening at the same time. It's like trying to juggle a bunch of different tasks without dropping any of them.
Okay, I can see how that would get tricky, especially as systems become more and more complex. How do we even begin to wrap our heads around concurrency without getting lost in the weeds?
Well, Lampson breaks it down into a spectrum. On one end, you have what he calls really easy concurrency, where tasks are either completely independent or they communicate through very simple mechanisms.
Okay, so each task is like its own little island. No overlapping or dependencies to worry about.
Precisely. Imagine dividing a big task into smaller chunks that can be worked on simultaneously. It's like having a team of chefs working on different parts of a meal at the same time.
I can definitely see how that would speed things up. Divide and conquer, right?
Exactly. And a classic example of this in the computer world is sharding a database. You split the data across multiple servers so each server can work on its own portion independently.
Okay, that makes sense. So what about the other end of the spectrum? What does hard concurrency look like?
That's where things get really hairy. We're talking about situations where even the smallest actions can interact in incredibly complex ways. It's like trying to untangle a giant knot of Christmas lights you pull on one strand, and suddenly everything else is affected.
Oh, I've been there. Sounds the kind of thing that would give even the most seasoned programmer nightmares.
It can definitely be a challenge. And in these scenarios, you often need rigorous testing, formal verification methods, even mathematical proofs to ensure that everything works correctly, even when multiple processes are jostling for resources and potentially stepping on each other's toes.
So you're saying there's a whole branch of computer science dedicated to proving that concurrent systems actually do what they're supposed to do.
Absolutely. It's a fascinating and essential field because as our systems become more complex and interconnected, concurrency is only going to become more important. And, there's a lot of ground between really easy and really hard. That's where the sweet spot for practical concurrency lies.
And that sweet spot, as I'm hearing it, is all about finding ways to make complex actions appear atomic.
You got it. Atomic in this sense meaning unbreakable, indivisible. It's like creating these little isolated bubbles where everything happens in a predictable sequence without interference from other parts of the system.
So it's like saying, okay, everyone pause for a moment while we complete this one crucial task, then you can all resume whatever you were doing.
Exactly. And a key concept here is the lock invariant, which basically defines the rules of the game for these atomic actions. It's a way of ensuring that while the system as a whole might be in constant flux, those critical operations happen in a controlled and predictable way.
Okay, this is starting to make sense, but I always appreciate a good, concrete example to really drive the point home. Got any up your sleeve?
Think of a database transaction, like transferring money between bank accounts. You want to make sure that either both the debit and credit happen or neither of them happen. You don't want money disappearing into the ether because of a system glitch.
That would make my banking app a lot more stressful to use, that's for sure.
Exactly. And that's precisely what atomic transactions, with the help of lock invariants, help to prevent. They guarantee that even if multiple transactions are happening concurrently, they won't interfere with each other in a way that compromises data integrity.
So it's about maintaining order, even in the midst of chaos.
Precisely. And to further enhance this control, Lampson introduces the concept of epochs in system design.
Epochs. Okay, now you're going to have to explain that one. I'm picturing hierarchical time periods.
Not quite. Think of an epoch as a defined period of time where a specific rule or invariant holds true. It's a way to create temporary stability within a dynamic system, like hitting the pause button on certain types of changes to make things more manageable.
So it's like saying, all right, for the next 5 minutes, no one can delete any files. We need to perform some maintenance, and we don't want any data accidentally disappearing.
Exactly. It's about creating these little pockets of predictability within a larger system that might be constantly in flux. It's a powerful technique for managing complexity and ensuring that even in a highly concurrent environment, certain critical operations happen in a controlled and predictable way.
Okay, so we've covered simplicity, we've delved into efficiency, and we've even braved the wild world of concurrency. But there's still one big piece of the puzzle missing, right? The what if everything goes wrong part.
Because let's face it, in the real world, systems crash, hardware fails, software bugs rear their ugly heads. It's not a matter of if, but when.
Exactly. So how do we build systems that can withstand those inevitable failures? That's where dependability comes in, right?
Absolutely. And this is where Lampson's paper really shines. He doesn't just talk about preventing problems, he talks about building systems that can gracefully recover from them.
Okay, so it's not just about building an impenetrable fortress, it's also about having an escape hatch, just in case.
Precisely. And the key to achieving this, according to Lampson, is redundancy.
Redundancy. So like having a backup generator kick in if the power goes out.
You got it. It's about doing things multiple times, either in time or in space, so that if one attempt fails, there's another one ready to take over.
Okay, that makes sense. So redundancy in time would be like retrying an operation if it fails. And redundancy in space would be like,
Having multiple copies of your data or services, like in a RAID setup for hard drives.
RAID. Now that's a blast from the past. I remember setting up my first RAID array. It was like having a safety net for my data.
Exactly. RAID is a classic example of redundancy in action, and Lampson points out that this principle applies to all aspects of system design. Whether you're talking about hardware, software, or even entire data centers, redundancy is key to building truly dependable systems.
So the goal is to eliminate those single points of failure, those if this one thing breaks, the whole system goes down scenarios.
Exactly, because no matter how carefully you design and build your system, there's always the risk that something unexpected could happen. A power surge, a hardware malfunction, even a rogue squirrel chewing through a cable.
Okay, you got me there. Rogue squirrels are pretty hard to predict, but finding those potential points of failure must be incredibly difficult, right? It's like trying to predict every possible thing that could go wrong.
It definitely takes careful analysis and a deep understanding of your system, its dependencies, and its operating environment. Lampson actually shares some pretty gripping real-world examples of single points of failure, and the consequences can be, well, pretty dramatic.
Okay, I'm listening. Hit me with an example.
Remember the Ariane 5 rocket disaster?
The one where the rocket exploded shortly after launch. That was a single point of failure.
It was. A single software error caused a chain reaction that resulted in the rocket veering off course and self-destructing just 40 seconds after liftoff.
Talk about a worst-case scenario. So redundancy is about more than just having a backup plan. It's about anticipating those potential points of failure and designing them out of the system from the get-go.
Precisely. But even with the best redundancy in place, things can still go wrong. So it's not just about having a backup, it's about how quickly you can recover from a failure.
So minimizing downtime, making sure those failovers happen seamlessly and ideally without the user even noticing that anything went wrong.
You got it. That's where metrics like mean time to repair or MTTR come into play. It's not about how long it takes to fix the original problem, it's about how long it takes to switch over to a redundant component and keep the system running smoothly.
Got it. So it's kind of like those self-driving cars that are constantly scanning their surroundings for obstacles. If something unexpected happens, the system needs to react instantly to prevent an accident.
That's a great analogy. It highlights the importance of real-time monitoring and fast failover mechanisms. But it's also about understanding those failures, not just reacting to them. Lampson stresses the importance of having a system for analyzing failures, digging into the root causes, and figuring out how to prevent similar incidents from happening in the future.
So it's like having that black box on an airplane. If something goes wrong, you can analyze the data and figure out what happened, which helps make air travel safer for everyone.
Precisely. It's about learning from those mistakes and constantly improving the system. And, this whole discussion of dependability ties back into our earlier conversation about atomic actions.
Right. Atomic actions. Those little bubbles of predictability in a chaotic world, what do they have to do with dependability?
Well, remember our bank account example?
How could I forget? I'd rather not have my money disappearing into the digital void.
Right. So atomic transactions are crucial for ensuring data integrity, especially in a system that's designed to be dependable. They follow these four key properties: atomicity, consistency, isolation, and durability, or ACID for short.
ACID. Okay, that's a pretty good acronym for something that's protecting valuable data. But Break it down for me. What do those properties actually mean?
Sure, atomicity means the entire transaction happens or none of it does. Consistency ensures that the transaction leaves the system in a valid state, meaning no broken links, no corrupted data, everything's still working as expected. Isolation means that concurrent transactions don't interfere with each other, so you don't end up with a situation where two people think they've booked the same flight or withdrawn the same money from an ATM. And durability means the changes made by the transaction are permanent, even if the system crashes right after you hit save or submit.
So it's like having a super secure vault for your data, complete with multiple locks and a team of guards watching over it 10/27.
Exactly. And one of the key mechanisms for achieving this level of security is the concept of prepare.
Prepare. Okay, now you've really got my attention. Tell me more.
So, before making any irreversible changes, the system basically does a dry run, making sure that all the necessary steps are in place, all the resources are available, and everything is good to go. It's like a final dress rehearsal before the curtain goes up.
And if anything goes wrong during that prepare phase, you could just abort the whole thing and start over without any lasting damage.
Precisely. It's like hitting the undo button before you've actually made any changes.
Hmm.
And when you have multiple systems involved, like in a distributed database, they use a consensus protocol to agree on whether to commit or abort a transaction.
Consensus protocol. So it's like a group of experts coming together to make a decision. If they all agree, then and only then does the transaction go through.
Exactly. It's a way of ensuring that everyone is on the same page and that no data gets lost or corrupted in the process.
Okay, that makes sense. So we've covered redundancy, we've talked about recovery, we've even touched on atomic transactions. Is there anything else that falls under this big umbrella of dependability?
Well, no discussion about dependable systems would be complete without talking about security.
Ah, yes, security. Because what's the point of building a system that can withstand a hurricane if it can be brought down by a stiff breeze of malicious code?
Precisely. And Lampson doesn't shy away from this topic. He argues that security should be baked into the design of a system from the very beginning, not treated as an afterthought.
So no bolting on a security system as an afterthought.
Exactly. It's about anticipating those threats early on and building defenses into the very fabric of the system. And that starts with a solid threat model.
Threat model. So like a list of all the bad guys who might be trying to break into our system.
Not exactly a list of names and faces, but you're on the right track. It's about identifying who the potential attackers are, what their motivations might be, and what methods they might use to try to compromise the system.
So you need to know your enemy.
Exactly. Once you understand the threats you face, you can start to build defenses against them. But Lampson also emphasizes the importance of what he calls a respond mindset, rather than trying to prevent every possible attack.
Respond. So it's not just about building an impenetrable fortress. It's about having a plan for when that fortress inevitably comes under attack.
Precisely. It's about having backups, auditing mechanisms, and recovery procedures in place so you can minimize the damage and get back on your feet quickly if a breach does occur.
So it's not about living in a constant state of paranoia, but about being realistic about the threats and being prepared to deal with them.
Exactly. And when it comes to actually building secure systems, Lampson highlights two main approaches: high assurance and fixing bugs.
High assurance versus fixing bugs. Okay, those sound like two very different philosophies.
They are. High assurance is all about building a small, simple, and verifiable, trusted computing base. You're essentially trying to create a system that is so well designed and well understood that it's practically impossible to break.
So it's like building a fortress with walls so thick that nothing can penetrate them.
Exactly. But the downside is that building such a system is incredibly difficult, time-consuming, and expensive.
So high assurance is like the gold standard of security, but not always practical or achievable in the real world.
Exactly. That's where fixing bugs comes in. This approach is more about finding and patching vulnerabilities as they're discovered. It's a never-ending game of cat and mouse, but it's often the most practical approach for large, complex systems.
So high assurance is like building a fortress, and fixing bugs is more like having a really skilled repair crew on standby, ready to patch up any holes that might appear.
That's a great way to put it. And in the real world, most systems use a combination of both approaches. But regardless of your approach, Lampson emphasizes the importance of isolation.
Isolation. So like keeping your systems locked down, separated from the outside world as much as possible.
Exactly. It's about limiting the damage that can be done if a breach does occur. Imagine a ship with separate, watertight compartments. If one compartment gets flooded, it doesn't mean the whole ship sinks.
Ah, compartmentalization. Contain the damage, prevent it from spreading. That makes sense.
Precisely. But Lampson also points out the challenges of what he calls side channels.
Side channels.
Mm.
Okay, now you're going to have to explain that one. I'm picturing secret passages in a medieval castle.
You're not far off. Side channels are these sneaky ways that information can leak out of systems that are supposed to be isolated. They're often overlooked, but can completely undermine your security measures.
So it's like thinking you've locked all the doors and windows, only to discover that there's a secret tunnel leading right into the heart of your castle.
Exactly. And it highlights the fact that building truly secure systems is an ongoing process, not a one-time event. You need to be constantly vigilant, monitoring for threats, patching vulnerabilities, and adapting to new challenges as they arise.
So it's like a game of chess, constantly trying to anticipate your opponent's next move.
Precisely. And speaking of anticipating moves, let's shift gears for a moment and talk about that all-important yummy factor that we touched on earlier.
Ah, right, yummy. The most important part, some might say. Because what's the point of building these super secure, dependable systems if nobody actually enjoys using them?
Exactly. Lampson argues that user enthusiasm is essential for a system's success. It's about making technology that people not only rely on, but actually love to use.
Okay, so how do we do that? What makes a system yummy?
Well, Lampson points to companies like Apple, known for their elegant and user-friendly products, and Amazon, with their relentless focus on the customer. It's about sweating the details, creating interfaces that are intuitive and enjoyable to use, and always putting the user's needs first.
So it's not just about functionality, it's about the whole experience. It's about how a system makes you feel.
Precisely. Lampson emphasizes the importance of predictability, discoverability, and a focus on user intention in UI design. He argues that a well-designed system should feel like an extension of the user's will, not a barrier to be overcome.
So it's about making technology that's both powerful and approachable.
Exactly. And one approach that Lampson advocates for is Amazon's working backward method.
Working backward. Okay, I'm intrigued. Tell me more.
It's a design philosophy where you start by defining the ideal user experience, and then you work your way back to the technical implementation. You essentially create a mock-up of the finished product, though with all the bells and whistles, and use that as your roadmap for development.
So it's like having a clear picture of the destination before you even start planning the journey.
Precisely. And this approach can be incredibly powerful because it forces you to think about the user's needs and expectations from the very beginning. And, throughout this entire process, whether you're focusing on simplicity, dependability, or that all-important yummy factor, Lampson stresses the importance of an incremental approach to system design.
Incremental. You mean building a system in stages, piece by piece, rather than trying to create the whole thing in one go.
Oh. Exactly. It's about starting with a solid foundation and then adding to it gradually, testing and refining along the way.
So it's like building a house, brick by brick, rather than trying to airlift the entire structure into place in one go.
Precisely. And this approach allows for flexibility, experimentation, and course correction along the way. It's about embracing the journey, not just racing towards the destination.
This entire deep dive has been incredibly insightful. I feel like I've gained a whole new appreciation for the principles behind the technology I use every day.
Me too. Lampson's paper is a treasure trove of wisdom, and it's more relevant today than ever before.
So as we wrap things up here, what's the key takeaway for our listeners? What's the one thing they should remember from this deep dive?
That's easy. Whether you're building a website, designing a database, or even just organizing your own files, remember Lampson's wisdom. Strive for simplicity, embrace good enough, anticipate failures, and never lose sight of that yummy factor.
And remember, building great systems is an ongoing process. Never stop learning, never stop experimenting, and never stop seeking that perfect balance between form and function. Thanks for joining us on this deep dive into Butler Lampson's hints and principles for computer system design. Until next time.